Welcome back, everybody, for second half of the morning, building into lunch. Don't forget, though, at the conclusion of the next two presentations, we'll have the award ceremony, which is always exciting and fun to see the next generation of scholars in our field. The next two talks, I think, are going to complement the last one in the sense that, as you know, it's not just traffic and exhaust from the tailpipe, but you heard about brakes, etc. Road dust is included in that, and Dr. Coker will talk about that, and then Dr. Melger will talk about plastics, which were alluded to. So I think that's coming together really nicely. As I said, Dr. Eric Coker, who's been here, I don't know, maybe a year, time flies with the pandemic and everything, but a year or two, or maybe even three, I'm sure he'll tell you, but we're very happy to have him here in our midst, not only on a day-to-day basis, but today. He's working with the CDC, with Sarah Henderson and others. He's also an adjunct professor at the School of Population and Public Health at UBC. His training is fantastic, as you can see, across epidemiology and exposure science. He has had a prenatal focus. I don't know that that's going to be his focus today, but we will find out. Eric was, thank you. Come on up, Eric.
Thank you for the invite to be here. So I'm going to, first of all, very honored to share stage, although they're not technically here right now, but to share stage with Rima and Mike and others who have presented later on today. But today I will be talking about the unpacking the chemical and meteorological profiles of road dust in Prince George, BC. How many of you know where Prince George, BC is? Okay. I got to start working at BC CDC less than a year ago, so just in July, and okay. And so I had never heard of Prince George before I got here, and this project was kind of as soon as I got here, it's like, can you figure this out from a quantitative standpoint? And one thing that I was interested in is the meteorological profiles in addition to the chemical mixtures that we see in road dust. And so this work kind of tries to integrate that. And I don't have all the answers, but I will talk about potential climate change implications as well. But I don't think anybody has answers to any of this stuff. But we have inklings of, and I'll give you some inklings on my end. Is this what I use? Yeah. So all of you in BC, from BC, I'm not from BC, my apologies. You all know about road dust better than I do probably, and so right now throughout largely the interior of northern interior of BC, there's currently active road dust warnings. This is an example. There's one that's been ongoing in Burns Lake. There's two that recently popped up in Vanderhoof and Smithers. Again, I'm still learning the geography. So these active, this is from BC Ministry of Environment, these are active road dust warnings. So this is a common problem in BC. And it's not just specific to BC, but it's something that's very region specific within BC as well. And it's a growing problem. I won't get into all the details of road dust because I think Rima touched on it sufficiently enough, but suffice it to say, of course, there's airborne earthen material in dirt. That's a piece of road dust that's going to be inevitable because road dust is things that just settle on the road essentially. But the composition is really, really important. Particularly, there's the coarse fraction, which predominates for road dust. But as Rima pointed out, there's also ultrafines and PM 2.5. But fundamentally, it's a complex mixture of man-made and naturally occurring pollutants. Again, not to go over this ad nauseum, but there's road traction material, wear of road surfaces, brakes, and tires, which we've already heard about. But what you don't see in LA, obviously, is the road traction material for snow, although maybe a couple weeks ago they had to figure something out. But clearly, the road dust composition will vary geographically based on what's around locally, what's happening, local meteorology. I guess the main point to make here is that it's really a complex interplay of weather, what's happening meteorologically, the road surface itself, and the local traffic conditions. And of course, that's going to vary widely regionally within regions. So road dust is, I like to say, not all PM 2.5 is created equal. Not all road dust is created equal as well. That point stands. So again, this point has been made, all right, so I don't have to rehash this. And in fact, you've already seen this image here, but PM 2.5 has been going down throughout Canada, North America more broadly. So that's a mini success story, you could say. But that also means that the coarse fraction is growing in importance. There was some recent work done, some near road and far road sampling in Vancouver and Toronto that tried to kind of, look at differences in near road and further away from the road and what is the chemical composition and do some positive matrix factorization. You've heard that phrase today already. But the idea behind PMF is you're going to do some source apportionment. What is the source of these particulates, essentially, is what it's trying to answer. And so for both Toronto and Vancouver, you see they measured both PM 2.5 and the coarse fraction, which is that PM 10 to 2.5. You're essentially kind of, in some cases, you're subtracting out that PM 2.5 fraction. But what you see is for PM 2.5 and coarse fraction, at least in Toronto and Vancouver, you see much different profiles in terms of what is the source of PM. If we look at the coarse fraction, we can see it's dominated by mineral and road dust. There is a fair amount of brake and tire wear, which is that gray piece of the slice of the pie. So it's definitely not inconsequential. When we look at PM 2.5, it's these regional local industry that seems to be predominating, at least at these near road sites that were assessed. And then the same thing that Remo pointed out, they did see this kind of gradual decline of road dust signature the further away you go from roadways. I don't think that's shocking. We would expect that, but certainly they observed that. So what's going on close to roads matters in terms of road dust, or at least is more impactful. And I just also want to point out the areas that we see the most impactful PM 2.5 for our region, at least that are kind of chronically dealing with PM 2.5 elevated levels. We see the coastal, the central interior and the southern interior tend to be dealing with this problem more frequently. And of course, wildfire is a piece of that story. And then another chapter of that story is road dust. But I want to talk a little bit, so a lot of the talking today has been really, really good, big picture stuff, so this is going to be definitely more narrow focused. So I hope you can appreciate that since we're all in BC. But we're going to be drilling down on the context of PM 2.5 and PM 10 in Prince George, BC. And so for those that don't know, Prince George is in kind of the central, northern interior. I recently learned that. But that graph, you can't see it very well, but basically it's showing that national North America trend of lowering PM 2.5 gradually for Prince George. I wouldn't say it's market, but it seems to be going down. But some recent modeling was done for Prince George, BC. You probably can't see this very well, but I'll just walk you through it and say the main takeaway is that road dust seems to be a major driver of PM10 levels for Prince George, BC. Each one of those bars represent a different modeled location for PM10 in Prince George, BC. And so that light kind of orangish gray, I'm terrible with colors, the beige or something, whatever that is. Somebody correct me, please. No, that's basically, they've attributed that to road dust, but it's not the same year round. and this is ignoring wildfire impacts because that's such a sporadic thing, although you could say it's commonplace now, but it is fairly sporadic, and so they couldn't really model that. So this is excluding wildfire, so don't misperceive that. But what they found is that it's really during springtime, and in the upper right-hand quadrant there, that's where you see road dust impacts more pronounced during the springtime for Prince George, BC. So this study really focuses on the springtime road dust. And what are we in right now? So very timely, we're in spring, and we have road dust warnings going on in the interior and central interior of BC. So I would say this presentation is like spot on in terms of what's happening right now. And then there was some really good work done by Sarah Henderson's group at BC CDC, where they looked at the seasonal ambient particulate matter and population health outcomes among communities impacted by road dust in British Columbia. And you can see the map on the left is showing you the gray areas where they actually did this study. They were really interested in that coarse fraction. So road dust is that signature for springtime. And they really saw it in the data. It may not be easy to see here, but that upper chloropleth looking thing, that is for PM 2.5, and you see the wildfire season. You can also see the wood burning season as well for PM 2.5 is strong, but I just want to highlight that that's the red box there. I'm highlighting the wildfire season essentially. And then on the lower plot is the coarse fraction, and in the yellow box I'm highlighting that springtime is when we see the coarse fraction predominate for Prince George, BC. And you can see Prince George was a part of the study. Basically 7 different communities in the central and interior of BC. And then really interesting findings, they were looking at mortality, and the interesting thing that they saw was that it's probably difficult to see in this graph, but the takeaway is springtime road dust had about a 3% increase in mortality, and then PM 2.5 during the springtime didn't have that same impact. The graph on the bottom is showing that it was, during its wildfire smoke that is driving the mortality during the summertime. But it really, this paper does a good job of highlighting this seasonal component in terms of the PM 10 makeup. It's, varies in terms of what's dominating seasonally. So springtime, it's coarse fraction. And also, this raises the idea that air pollution risk has a seasonal component to it in terms of health outcomes. And so that was the motivation sort of the study that I'm going to talk about. I also want to point to a paper that came out a few years ago that analyzed the health effects from simultaneous exposure to physical and chemical properties of airborne particles. And this was a study done in London. And they implemented a method called Bayesian profile regression, which is essentially a cluster analysis. But the nice thing about it is you can, with this model fitting, you can estimate health outcomes in relation to these different clusters. And so they measured chemical components, physical properties of the particulate matter throughout London. And so each one of those panels there represents a different cluster that was detected in looking at the chemical, physical properties of the particulate matter. And somewhat similar to the paper by Sarah Henderson's group. What's that? Oh, well, I was not then part of the group then, but I am a Henderson group person. So A, B, C, those different panels or different clusters that were identified from this analysis, they did fit, they were looking at respiratory mortality in particular, and the only cluster that showed a signal for increased mortality, was this cluster C, so the third cluster, which it's difficult to see here, but coarse fraction was elevated during those days, as was PM 2.5. Those are not absolute numbers; those are z-scores, just because it had to normalize everything, so it makes sense. But another interesting thing was that was about a 2% increase in respiratory mortality for that particular cluster. The days were characterized by high non-primary PM in particular, and the coarse fraction was quite high on those days in those clusters. And most of those days were in the spring, with some of the days happening in fall. Again, London, obviously, this is a very different city than Prince George, BC, so I'm not trying to make a direct comparison here. But there's this signature in terms of clustering of the chemical composition and a seasonality component to it. And the excess mortality was tied to the occurrence of these mixtures at different time periods. Also, we did some work in Los Angeles County where we modeled the spatially varying effect of PM 2.5 on low birth weight in Los Angeles County. This was part of my dissertation, and what we did is we kind of used a random slope model, and we showed that the effect of PM 2.5 varies spatially even within a region. So as Mike illustrated, there's this, supra-regional variation, but even when we look at a single or large urban metropolitan area, we see spatially significant differences in the effect of PM 2.5 on low birth weight. So the next chapter of my dissertation said, well, could the air pollution mixture maybe explain some of that? Could also the makeup of who the people are that live there, could that explain some of this? And so I applied this same Bayesian profile regression cluster analysis method that London paper did, and we identified 13 different kind of air pollution mixtures throughout Los Angeles County. So that complex map on the left, it's probably to figure out what's going on there, but just to say that there's many different mixtures throughout Los Angeles County. And these are pregnancy-specific exposures. We can see a distinct pattern of highways having an interesting mixture, and I'm not showing the data, but basically just know that it's a really, really high PM 2.5, high NO2, high NO by these roadways. That's not surprising, but when we go to model the health effects of these different clusters, this map on the right is showing, this is set in a Bayesian context, and so we can kind of look at the probability of adverse birth outcomes based on cluster. And this is showing you areas in dark brown or places with really, really high probability of adverse effects on low birth weight. And it's a pretty obvious pattern that the effects appear closer to roadways, in particular major roadways. There was a signal in the data suggesting that it's primary pollutants. These were all elevated for NO and NO2. That, again, not surprising, close to roadways. But it also raises the question is, probably road dust is a component of that. The brake wear, tire wear is a component of that PM 2.5. So for LA County at least, there's spatially varying effects of PM 2.5 on adverse birth outcomes, and the mixture varies widely across the county, and the effects kind of vary widely based on the chemical mixture. So now I'm going to transition to the study that I'm actually here to talk about, so after going through that context. This study really focuses on springtime road dust season in Prince George, so where we are now in time. What we did is we measured daily contributions of, the goal is to measure the daily contributions of trace elements, including heavy metals, to near road PM 2.5. I'll talk about these methods in just a minute here. We wanted to explore the within season temporal trends of the coarse fraction and PM 2.5 that's comprising PM 10. We wanted to classify days with high levels of springtime road dust based on a threshold of the percentage of coarse particulate matter that comprises PM 10. And then finally, we wanted to identify the chemical weather profiles of days with high levels of road dust. So trying to accomplish a lot from one monitoring location, but it was a really excellent study designed by Sarah Henderson's group, which I'm a part of. But this sampling all happened before I got here. But so this is kind of like my first task when I got here. We had some hypotheses when I took on this analysis. I hypothesized that PM10 is characterized by high within-season variability of chemical mixture composition. Chemical mixtures vary significantly between high road dust days compared with low road dust days, and that PM10 chemical mixtures cluster together with distinct meteorological profiles. Those are kind of the three underlying hypotheses that we're looking at. So a little bit more about the study setting. So Prince George, BC, you can see it's almost like in the heart of British Columbia a little bit. It's highlighted in red there. Is there a pointer in this? No? Okay. Nevertheless, we had two monitoring locations. One that was for our study site, which was a near road site, which is that square-looking red point. And then there was a NAPS monitoring station, so a National Air Pollution Surveillance Network for Canada. We use that as kind of like a reference site and to supplement our monitoring. So we monitored for PM10 at the near road site. We did 24-hour sampling. During the wintertime, it was Tuesdays and Thursdays, but during the springtime, we switched to daily measurements of PM10. So we used a high volume sampler. The advantage there is we can actually detect the chemical composition on a day-by-day basis. If I just put a normal sampler out there with drawing in air, I'm probably not going to get enough material to detect these. Even though we have sensitive instrumentation, it's really hard to detect. And somebody said money out there. Yeah, there's money thing as well. Nevertheless, we also use data from a nearby weather station that's run by Environment Canada. And so the NAPS monitoring station, we use the hourly data so we can match up in time the daily samples that we had for the study site, near road study site. And again, we use the temperature, humidity, precipitation, wind speed, wind direction, and dew point data that's provided by the nearby meteorological station. We worked closely with University of Northern British Columbia that's actually based up in that area. Their laboratory, the Northern Analytics Lab, did all the analysis for us. They did the mass concentration of the PM10 samples. They did the filter extractions for us. So they extracted those PM for the chemical analysis. And then they did ICP OES with very kind of really low detection, high sensitivity. Basically, if something had high lack of detection, so 75% or more, we threw those samples out. We couldn't really use those from a statistical standpoint. All other samples that had reasonable detection levels but were below detection, we just imputed those values. Or not, rather than have them missing, we did LOD divided by the square root of 2. I won't talk in detail about the data analysis, but just know that a lot of our analysis focused on the near road study site and the NAPS monitoring site. We did our conventional kind of what are the averages of these different chemicals and the averages of the PM10 and the PM2.5. And so the interesting thing about the NAPS site, it measures both PM2.5 and PM10, so we can use that information to get a coarse fraction. So while we didn't get coarse fraction at the actual near road site, we could infer by the near very close by NAPS site the level of coarse fraction kind of in the study area. We did linear regressions and correlation analysis just to establish the relationships between all the meteorological chemicals and PM measurements that we came up with. I will note that we calculated a metric, which is the percentage of PM, the percentage of coarse fraction that comprises PM10, and we established a threshold of 65% or more would be a high road dust day. if you have questions about that, we can talk about that. But the main point of the analysis, we did this cluster analysis, and we're able to identify the kind of clustering of meteorology and chemical signatures of the road dust. And so we measured 16 different trace elements, including heavy metals, as I mentioned. So now we'll jump into the results. Just to point out that this graph is showing you this seasonal component. The blue line is PM 2.5 at the NAP site, and the blue line is coarse fraction, and you can see this kind of switch going on. It's almost like you turn a switch in mid-March, and all of a sudden, coarse fraction is dominating in Prince George, BC, at the NAPS monitoring site. This is not shocking. This is why we're doing the study. But that signal is definitely there in the data. This graph is just showing you where we've classified days by different high road dust, low road dust, which is the green, and then unclassified, because there was a day where we were kind of missing a little bit of data at the NAP site. So that graph is the near road study site, and you can see low road dust days during the winter, and then we get high road dust days occurring during the spring mostly. And on the y-axis, that's PM10 concentration from the high volume sampler at the near road site, and then the graph down below is at the NAPS monitoring site. And what we're showing here, we're trying to depict, is the percentage of PM10 that is either PM 2.5 or coarse fraction. The blue is the coarse fraction, and the red is the PM 2.5 portion of the PM10. These are just a lot of different PM metrics, but they are distinct things we're trying to show. And you clearly see that profile flipping, and this is daily data, and you see that profile kind of switching as you go further into the springtime period, and this consistent indicator of road dust. Now, this graph, there's a lot going on, and I can't kind of go into all of it, but suffice it to say that the proportion coarse fraction and the PM and the coarse fraction concentration are highly correlated with humidity in particular. That was the main kind of predictor, I would say, of the meteorological variables that we're considering. Not surprising here, like dry days, this resuspension of road dust is more liable to happen. So I don't think that's a surprise. But for our PM10 high volume sampler, that near the roadway, there's an even stronger relationship with humidity. So at the NAP site and the PM10 high volume near road site, we see a very strong relationship with humidity. There's other meteorological variables that are important, but precipitation is particularly important at the near road site, but not so much for these other metrics, which is kind of interesting. The graph on the right is even more complex to look at, and I apologize for that, but we measured a lot of trace elements, and so this is the world of mixtures, right? So I'll just point out that humidity and precipitation really do show the strongest relationships with these different trace elements. You can see the correlation between the different metals and whatnot. I will point out that copper, and people that know more about this than me, copper was really the one that stood out. You can see it doesn't have very many shared sources. That's listening to Rima, that's probably the brake dust stuff, right? Needless to say, but I'm going to say it anyways. I don't know, why do we say needless to say? So, and then we just say it. So, this stuff is very complex, and we have to go a little bit beyond our conventional analysis frameworks. I will say that when you just kind of simply stratify by high road dust days and low road dust days, clearly high road dust days have much higher PM10 on average. So the red is the high road dust days, and the blue is the low road dust days, so the graphs on the top. And then, so the one on the left is daily PM and PM10, and then the one on the right is the sum concentration of all the measured constituents that I just showed you on that previous graph, right? All of these 16 trace elements. So clearly, there's a statistically significant difference in PM10 and some of the constituents. Okay, not shocking. When we dichotomize these by high road dust, low road dust days, the graph on the right is just, or below, is kind of like a giving you this more comprehensive look at the contrasting of the high road dust, low road dust days, much higher concentrations for all of the metals that we're looking at, except for perhaps copper. And then, but we can see there's different relationships between the meteorological variables and the, well, not different relationships. There's different patterns of meteorological factors between high road dust days and low road dust days. But this is a very kind of crude way of looking at the data, just saying this is high road dust, this is low road dust. The cluster analysis here is where it becomes important to disentangle this a little bit more to really understand more clearly what could be going on. So the cluster analysis resulted in a total of 5 clusters. And so these are daily. So this is like kind of, it's almost like taking a time series data set, or it is taking a time series data set and doing cluster analysis. So days are clustered together based on their similar occurring patterns of levels of PM10, levels of trace metals and elements, levels of meteorological factors. That's essentially what we're doing. Like, what are, like, on one day is it high, 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 and one day is it low, 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 low for all of these different variables. But trying to reduce that dimensionality to try to understand better what's going on. Cluster 4, I highlight in red here, that is the cluster that where 93% of the days, also almost every day of the, could be classified as high road dust days. And then PM 2. So the reason why that is because 75% of the PM10 is the coarse fraction. So this cluster analysis really did do a good job of saying, okay, these are the days that are clearly road dust days dominated by the coarse fraction. And then of course the PM10 high volume sample concentrations on average were 48 micrograms per meter cubed, so quite high on those particular days. Now, this same heat map, and so instead of just dichotomizing high road dust, low road dust, this is a more data-driven way to say how do these variables come together and what are the profiles or what are the mixtures, how do they look like in cluster 4? We can see they're quite distinct from these other types of clusters. You can see it's elevated for pretty much every PM metrics that we assess, but particularly so for the coarse fraction and the proportion that is coarse fraction, and then all of the trace elements are elevated except for copper. That's just kind of middling. We can see, I guess one thing I failed to point out here. Okay, good. So just make the point that temperature and humidity have this interesting interaction going on that kind of has some potential implications for climate change. This graph is just showing that these clusters vary significantly throughout the season. There's some temporal autocorrelation, and that days are more likely to be in cluster 4 in closer time together, but they do vary throughout the springtime season. So you can't just say that, chemical mixtures are going to be the same throughout springtime. It does vary on a day-by-day basis for the most part. So I will just have some concluding thoughts here. Cluster analysis of PM10 samples from the Near Road study site indicates that springtime PM10 comprises complex mixtures of trace elements. We expected to see this. The chemical composition varied significantly between high road dust days and low road dust days. We confirmed that hypothesis. Heavy metals of high public health concern were significantly elevated on high road dust days. Meteorological factors appear to work in combination to determine the occurrence of high road dust days, particularly humidity and temperature. So it's not just humidity, it's also, there's some evidence that the effect of humidity is temperature dependent. And then cluster analysis, of course, PM is its chemical composition combined with meteorological data has promised to improve the assessment of springtime road dust for exposure assessment in epidemiological research. I'm probably out of time, is that?
Yeah, I think I counted for
Okay, so I will do the hard stop. I had some just concluding thoughts about possible climate change implications, but we don't have time to get into that. If people want to ask, we can talk about it. So there we go. Thank you to the BCCD team, UNBC, and Health Canada, of course, for funding this study. Thank you. So everything was clear. That's good.
Well,
Okay.
There's somebody there.
I see a question in the back potentially. Yeah. They're gonna connect. They're gonna connect.
There you go.
In terms of the chemical compositions you were seeing, is there any link between that and the proximity of the pulp mill in the area for Prince George?
Proximity to what? I'm having
The pulp mill?
the pulp mill.
Yeah.
That's a good question. We didn't try to do like a source apportionment approach. I did look a little bit at wind. I did look at some wind roses and see like have wind direction and wind speed. Where do we see there was some obvious examples to look at from that data that there's a directionality of the trace elements and the coarse fraction. And actually the coarse fraction in PM 2.5 had kind of opposing directionality in terms of the probable sources. I didn't really delve into, okay, well, what are those potential sources? So I can't speak to that exactly, but I did try to look into it based on the available data. But it seems like something worth looking into. It was clear the coarse fraction was coming from, like, there's the major highway right there, and all of, unsurprisingly, the concentrations were in that, I guess, slightly northeasterly direction of where the major highway was. So that was definitely the source of the coarse fraction during the study period. But it's an interesting question about the pulp mill. See, I don't know these local factors, man. This is really important stuff.
Okay, we'll squeeze it in. Where are we? Michael Schwann, right? Okay.
Yeah, thanks very much, Eric. And I know you didn't have the chance within your time to talk about the climate implications that you had laid out, but could you take a moment to speak to the climate implications?
Yeah, so, I mean, I think I'm more coming from it from the standpoint of I don't have an answer to that question, more so what are the potential questions we might want to consider with climate change. First of all, higher temperatures was associated with higher coarse fraction, higher proportion coarse fraction. But temperature wasn't really related to any other PM metric that I assessed. So there's that point. So it appears that the coarse fraction was particularly sensitive to higher temperatures, whereas PM 2.5 was basically not when you control for all of the factors. So I did like a multivariable analysis. So there's that issue. Also, when we're talking about road dust in springtime, we're talking about snow melt. Will we see changes in the amount? Will snow melt earlier? Will humidity change in that context? In the context of climate change, there's basically a lot of unanswered questions about climate change and how it'll impact road dust, but there's some suggestion, this interaction between temperature and humidity. So with climate variability due to climate change, like how does that impact the exacerbation of road dust? I don't know the history of road dust events in Canada. I'm new to Canada and BC, but it would be interesting to see, do we see changes over time in terms of road dust events happening and our ability to detect them. So that's one issue. And also there's going to be this geographic variability, I would imagine, of if climate change is impacting the exacerbation of road dust, then there's going to be geographic variation in those impacts. So those are kind of some of the questions I would want to know. Is road dust going to be worse as a result of climate change? We don't know. The data suggests that it's sensitive to, road dust is sensitive to these climate variability. And if that's the case, where is that going to be more pronounced throughout British Columbia? Those are the kinds of questions I think are worth looking into.
Okay, thanks. I'm just noticing, by the way, these are pretty heavy. I don't know what's in there, but something substantial, so thank you.
Okay, cool.
Okay.